Let's talk about rockets for a bit. Specifically, we're going to talk about the ideal rocket equation and how you use it. The ideal rocket equation is fairly simple. Delta V for any particular rocket, in other words, how much velocity that rocket can provide, is equal to G0 times the specific impulse times the natural log of the initial mass over the final mass. And this little powerful equation, you can read the derivation in your book, Understanding Space. It's in one of the appendices. But let's talk about how we can actually use it. So in this case, for a rocket, what we typically say is that we have kind of three mass components that we kind of always have to consider. There's going to be the payload, there's going to be the structure, and then we're going to have fuel, or what we're going to do is we're actually going to call that propellant, and I'll talk about why we're going to do that later. So this is propellant. And then everything else, it's not the payload and not the propellant, so this casing here and everything else is going to be structure. So when we talk about the mass, initial, before this thing takes off and it's fully fueled, put some fins on here to make it look a little bit more like a rocket, the initial mass is going to be mass of the payload plus mass of the propellant plus mass of the structure. So when we take off, that's what our mass is. Now, we always assume when we're doing using this equation in this class anyway, is that the final mass is just going to be this minus the propellant. So we're going to take this element out. So the final mass is equal to mass of the payload plus mass of the structure, because all the fuel inside has been burnt up getting this thing into space. Let's put a little nozzle on here. All right? Okay. So let's do a quick example of how we would use this. Let's say we have a rocket and we want to send, let's say, 100 kilogram payload up, and we want to use, and you'll notice with rockets a lot of times the propellant is most of what of the entire body. We'll say we have 2,000 kilograms of propellant, and we'll say that the structural mass is going to be, 300 kilograms. I'm just picking these numbers out of the air. So our initial mass then is going to be everything, 2,400 kilograms. Our final mass is just going to be 400 kilograms. And now we're ready to plug into the ideal rocket equation. And G0, by the way, is always, no matter where you are, going to be 9.81. Oops, forgot my ISP. Times natural log of MI over MF. And, well, we haven't selected an ISP for this. We're going to assume it's a solid, and so the ISP for a solid is typically around a little over 200. So we'll say this is 210 seconds. And notice we have to have seconds here, because when we multiply our acceleration, G0, which is equal to 9.81 meters per second squared, when we multiply it by 210 seconds, the units work out and we get a delta V that is appropriately in meters per second. So when we do this calculation, and I'll do it here live, we have 9.81 times 210 times natural log of 2400 divided by 400, and we get a delta V that's 3,691.2 meters per second. So again, just by knowing some of the properties, the ISP is related to the fuel and the engine, how efficient this thing is at using its fuel. This is a given, it's always the same. And so based on just the ISP and the initial and final mass, we can determine how much total velocity this rocket can give us. And when you look back at your notes on launch velocities, in launch velocities we're determining how much would we need to get to a particular orbit that we're interested in. That's different from this. This is telling us how much we actually get. So 3691.2 is less than what we usually see for something that needs to get into orbit. Remember, a satellite has to be going at around 7.5 kilometers per second, or 7,500 meters per second, to be in orbit, and that's not counting all the losses that you incur when you're going up. So this is clearly not enough to get us to orbit, and later we'll talk about staging, and when you see rockets like the Saturn V and Atlas and these things that actually get things into orbit, they have multiple stages which kind of add together to give us those types of velocities we need to get to orbit.